light into darkness. When did the first stars appear? Were they very massive? And if so, how much? How did they influence the chemical composition of the universe? A few minutes after the Big Bang, the universe consisted of a dense, chemically poor plasma, made only of hydrogen, helium, and traces of lithium. As the universe expanded and its density and temperature progressively decreased, that primordial composition became frozen in time over eons. Roughly 400,000 years later, the density of the universe reached a critical value, such that matter became transparent to radiation. In essence, matter and light decoupled, taking different paths, evolving independently from each other. Light released during the coupling, a relic from the Big Bang, filled the universe with a brilliant glow. But following the expansion of the universe, photons from that light became stretched, carrying progressively less and less energy until they became microwave photons. Back then, the universe was devoid of visible light, a period known as the Dark Ages. Simultaneously, a myriad of electrons started to feel attracted by electrically charged atomic nuclei. This is when neutral atoms first appeared in the history of the universe, in an epoch known as the recombination era. These hectic early stages of the universe turned into a steady period of about 160 million years of darkness, which ended with the formation of the first stars and galaxies. Stars are born in groups. The history of star formation depends upon how much gas is turned into stars per unit time and the distribution of stellar masses at birth. Most of the stars in the universe have masses similar to the Sun, but there are also more massive and less massive stars. The gas out of which the first stars formed was primordial, that is, made only of hydrogen, helium, and lithium. It did not contain any heavier elements, known as metals in astrophysics, from carbon to uranium and beyond, since these elements are actually created by the stars themselves. In sharp contrast to planets, stars are powered by nuclear reactions and produce their own light. This requires central temperature of about million to billion degrees, which are achieved by compression of huge amounts of mass. The minimum mass required to form a star, or the Jeans mass, depends on the amount of metals in the contracting gas, since metals are a strong coolant. Since the Jeans mass is directly proportional to the gas temperature, it is expected that the first stars created in the hot primordial gas that filled the early epochs of the universe were really massive, reaching up to 300 solar masses, probably. These hypothetical stars, the oldest stars that ever existed in the universe, are known as population tree stars. The first generation of very massive stars polluted the cosmos with metals very soon. In fact, their formation stopped when a critical metal content, or metallicity, was achieved in the cosmic gas, about 1/1,000,000th of the solar value. Above such a critical metallicity, the Jeans mass decreased and less massive stars were produced thereafter. The existence of these long-gone first stars can be guessed by comparing the composition of the oldest stars in the galaxy with simulations of chemical evolution, where only a generation of massive and very massive stars is considered at early times. These models predict the evolution of the chemical composition of the gas in galaxies as due to stellar nucleosynthesis, star formation, and possible gas exchange with the intergalactic medium. In parallel, more and more very metal-poor stars are being discovered by sophisticated telescopes. To date, 14 stars with a very small metal content, about 10,000 times lower than that in the Sun, have already been discovered in the Milky Way. The first stars were so massive that they died in the form of titanic pair creation supernovae a few million years after their birth, shaking the fabric of space-time. Explosions of stars more massive than 10 solar masses are induced by a core collapse, leading to the formation of a neutron star or a black hole as possible remnants of the original object. Other supernovae involve the disruption of a white dwarf star in a binary system. In a pair creation supernova, the massive stellar progenitor can either explode and leave no remnant or implode into a black hole. Material ejected in the explosion of a massive star is expected to condense as soon as temperature decreases below 1,000 degrees. Smoking gun evidence of the explosion of a core collapse supernova before the solar system was born has in fact been found in ancient meteorites, and it will be reviewed in the next videos of Astronuclear Nibbles!